Hi everyone, I'm Diego Aranha from Aarhus University and I'm here to present LadderLeak, our latest attack against ECDSA signatures using less than 1 bit of nonce leakage. This work has already appeared at the CCS conference this year and it's available on ePrint. It's a collaboration with Felipe Novaes from University of Campinas in Brazil, Akira Takahashi from Aarhus University in Denmark, Mehdi Tibushi from NTT in Japan, and Yuval Yaram from University of Adelaide in Australia. In this talk, I will describe new attacks exploiting randomness, leakage, and bias from ECDSA-type signature schemes, based on newly discovered vulnerabilities in ECDSA implementations contained in the OpenSSL and LadderLeak cryptographic libraries. These vulnerabilities have led to theoretical improvements to the attack framework based on solving the hidden number problem. In the first part of the talk, I will explain how to acquire sidechannel information. In the second part of the talk, Akira will explain how to exploit sidechannel information to recover the secret key. But let's first start with some background on attacking ECDSA nonces. ECDSA and Schnorr signatures are among the most popular signature schemes relying on the hardness of the discrete logarithm problem for security. Modern instantiations of the signature schemes use elliptic curves for efficiency. In both of them, the signing operation involves a random value k, sometimes called a nonce, to randomize the signatures. Calling this value a nonce is a major understatement because it needs to remain secret or well protected for a long amount of time. Otherwise, the security of the signature scheme is completely undermined. Let's assume a scenario where Alice and Bob want to exchange digital signatures. So Alice generates a private key and sends her public key to Bob for verifying signatures. When Alice wants to sign a message, she generates a nonce and combines the nonce with the message and the private key to compute the signature that can be sent to Bob for verification. What's interesting about the signature scheme is that the signing equation relates public values coming from the signatures to the two unknowns, the private key and the nonce. This means that if the nonce leaks or is exposed somehow, this gives information to compute the private key directly. In particular, if two signatures are computed over different messages and using the same nonce, this can also be used to compute the private key. But these are extreme cases. For example, we could have the case that due to implementation error or malfunction in the random number generator, some bits of the nonce are fixed. Or perhaps an adversary is able to obtain leakage correlated with those bits with high probability. In this case, the adversary could collect many signatures computed by Alice under her private key and solve the hidden number problem to compute this private key. Randomness failure is not only of academic interest and can actually manifest in many different ways in the real world. Perhaps due to a poorly designed or implemented random number generator, or maybe the initial state of the random number generator was predictable, like a timestamp, or perhaps a virtual machine resets to a previous snapshot version and then repeats the internal state of the random number generator, producing the same nonce for two different signatures. In the context of this talk, I worry about sidechannel leakage, in which the attacker is able to obtain information correlated with bits of the nonce. One high-profile case of randomness failure in practice was the PlayStation 3, when Sony used the same nonce to sign many games, and this allowed the homebrew community to compute the signing key from just two different legitimate games, and then be able to authorize software to run on the platform. There are many other cases involving Bitcoin wallets and voting machines where randomness failure completely broken the security properties imposed on those systems. Our contributions in this talk are threefold. The first one is a novel class of cache attacks against ECDSA implemented in OpenSSL versions 102U and 110L, and also the research-oriented cryptographic library called LadderLeak version 0.4. There are many sets of parameters affected by this vulnerability. Essentially, any curve in which the group order is just below a power of 2 could be affected if the implementation is vulnerable as well. This includes many curves standardized by NIST and defined over prime fields, and also curves defined over binary fields. Also, some of the curves standardized in the older SecG standard could be affected. In particular, the Bitcoin curve SecP256K1. In the initial version of our work, we had the impression that curve P256 as implemented in OpenSSL was affected, but later we found out that OpenSSL has custom code to implement arithmetic on that curve that's not vulnerable. It's hard to know exactly what products are affected by LadderLeak, but we could search over GitHub and find that several projects bumped the library version of OpenSSL in their build systems. This means that they at least included versions of the library that were affected, but we cannot claim that this could be exploited under some realistic threat model against those products. The second contribution of our work is theoretical improvements to attacks based on Fourier analysis to solve the hidden number problem that significantly reduces the amount of input data or the number of signatures to be effective. This allows the attack to be feasible given less than 1 bit of nonce bias leakage per signature, which means that the attacker is able to obtain 1 bit of the nonce with less than 100% success probability. So then less than 1 bit of bias in average. We implemented a full secret key recovery attack against OpenSSL over 2 sets of parameters. A binary curve over a smaller field and a prime curve over field P192. Now let's move to some background on curve-based cryptography. Elliptic curves are sets of solutions x on y to a curve equation. And they come equipped with a geometric operation that defines a group law called point addition. When you want to add points P and Q, especially on this curve that's defined on the real numbers, so the curve is continuous, we can trace a line passing through P and Q and reflect the interception between the line and the curve across the x-axis to get the result. If the point is being doubled, we take the tangent line instead. And this allows us to compute R in the same way. For cryptographic interest, we take curves defined over finite fields, such that the discrete logarithm problem is hard. What's interesting is that the same geometric intuition gives us a group law, an operation that defines a group, in practice usually chosen to have prime order, with the point at infinity serving as the identity element. Efficient implementations will not represent the points on affine coordinates x and y, because computing the slope of this line requires to compute a field inversion or division that's computationally expensive. So actual efficient implementations will use a projective coordinate system instead, in which the slope of the line is accumulated across multiple operations and resolved only at the end. In this representation, a point is represented using coordinates x, y, and z, such that the x and y coordinates are weighted by some power of z. When elliptic curves are used to instantiate cryptographic protocols, one operation becomes critical, the so-called scalar multiplication. Scalar multiplication amounts to add the point G to itself a secret number of times. It is indeed critical for both performance of ECC crypto systems and their security. Let's take a look at the ECDSA signature generation for an example. So ECDSA signing takes a private key, a message, a group order, a base point, and a hash function as inputs, and it computes a valid signature. It starts by generating the nonce K that's then multiplied by the base point G to produce a point R. This point R is then used at the remaining steps of the signature to compute the pair of values that are produced as output. This operation here is actually sensitive because if there is any leakage about the nonce K, this can be used by an attacker to obtain information about the signing key. If one is worried in particular about timing attacks, in which the adversary monitors the execution time of intermediate steps of the computation to obtain information about K, a countermeasure is to implement this operation in constant time, such that the execution time doesn't depend on the bit pattern of K. This is very challenging on modern CPUs because they have instructions like cflush that can reveal secrets through cache data eviction. When programs share a library in memory, a flush and reload attack becomes possible. So assume that there are a victim and attacker programs running at the same time. And the attacker program is willing to know if a certain memory access is being performed or not by the victim's program. So for that to happen, the attacker flushes that memory address and then waits a certain number of cycles that we call the slot before it reloads that address to cache memory again. If the reload step takes a long time, this means that the victim process did not read that memory access. However, if the reload step takes short amount of time, this means that the victim's process actually read that memory access, and the adversary can use this information to distinguish between the two cases. Notice, however, that this attack is not deterministic in the sense that there could be overlaps between the memory access and the reload part, or some other cases in which it could be confusing for the attacker to distinguish between the two cases. That's why the attacker here is not assumed to obtain a 100% success probability. But the attacker will try to choose parameters that maximize the success probability, and we actually achieve over 99% probability in our cases. When implementing scalar multiplication in constant time, the Montgomery ladder algorithm is a prime candidate. It takes a point P as input, defined by a pair of affine coordinates x and y, and the bit pattern of the nonce k as additional input, and it computes the scalar multiplication of k times p. It works by initializing two accumulators R0 and R1 that are evaluated using the group law. Then it scans the bits of the scalar from left to right and performs some group law operations depending on the key bit. This algorithm benefits constant time implementations because no matter the value of the key bit, the same number of group law operations is called. Notice, however, that for a constant time implementation to be performed, we need to be careful about the order in which the points are input and are output in these instantiations or in these invocations of the group law. Another problem with this attack, as it's presented here, is the number of iterations of the loop that vary with the magnitude of k. So we need to find a way to fix this number of iterations as well. So a more realistic version of, or a more protected version of this implementation can be seen in this slide. First of all, before the scalar k is used, a multiple of the group order is added to produce a related scalar k prime that has fixed length, which allows us to fix the number of iterations of the loop as well. What's interesting here is that the way we add multiples of the group order preserves the most significant bit of k in the second most significant bit of k prime. Also, we need to be careful about the branches inside the loop, because there could be branch prediction or other microarchitecture features that leak information about the branch being taken or not. So actually, we can replace the branches with a conditional swap operation that will swap R0 and R1 without branches, depending on the bit of k prime being processed in this iteration of the loop. Typically, this conditional swap operation is performed in assembly to prevent interference from the compiler. Now, what remains for this implementation to be constant time is a careful implementation of the group law. LadderLeak is a vulnerability exactly on that part of the algorithm. So, and if you consider, for example, that R0 takes points P in affine coordinates and R1 computes 2 times P in projective coordinates, there is a source of leakage on the first iteration of the loop if the group law implementation is not careful. This is what actually inspires the logo we assigned to this vulnerability. For example, if the value R1 here can be distinguished by an attacker as being stored in affine coordinates, this leaks information about the points being swapped or not, which further leaks information about a bit of the scalar. The same observation applies to the point addition here that might take R1 in either projective or affine coordinates. If the attacker is able to observe these differences on the first iteration of the loop, it can actually split a large number of signatures in 2 sets, which are, from the attacker's perspective, biased because they share the same top bit in the scalar or in the nonce. Our experimental setup involved 2 Broadwell CPUs running at different clock frequencies, but both with turbo boost disabled for reducing noise in the measurements. The binaries were executed in userland runtime without requiring any privileges, and OpenSSL was built using the default configuration with debugging symbols enabled for a slightly more convenient attack. In terms of tooling, we used the frtrace binary from the Mastic Sidechannel Analysis Toolkit, which allows us to run flush and reload attacks. We configured the slot to be 5,000 cycles, which was enough for high precision. We also used the other idle cores in our platforms to perform a performance degradation attack, in which they evict code from cache to penalize performance and amplify timing differences between these different cases we observed on the previous slide. So let's illustrate this attack by examining how OpenSSL implements arithmetic on prime curves. In this particular case, the adversary will try to find out if point R1 inside the first iteration of the Montgomery ladder is stored in affine coordinates, which leaks during the point doubling operation, which leaks information about a bit of the scalar. OpenSSL actually optimizes for the case when point R1 is in affine coordinates by performing just a buffer copy when the coordinate Z is 1. Otherwise, it computes a full field multiplication using the coordinates. So the attacker starts 2 probes on 2 different parts of the code and measures the time it takes for reaching each of these probes. And by measuring the time from the first to the second probe, it tries to infer what type of computation happened in between. Observe that the performance difference between this line and this line is not very high, but actually a performance degradation attack can amplify the difference to around 15,000 cycles, which corresponds to 3 slots. So as a result, the attacker is able to mount a flush and reload attack that detects if PN copy is called, which means that the Z coordinate of the point is 1, which means that the point is in affine coordinates, which leaks a bit of the scalar. And this, in our particular case, this was possible with larger than 99% precision. Let's take a look at the memory traces for illustration. So in these graphs, the y-axis has the memory access time in cycles. And the threshold we used for a cache hit was 100 cycles. So anything below the red line is considered to be a cache hit. So the adversary monitors the scalar multiplication, and he observes 2 point doublings in affine coordinates in the case that the second most significant bit is 0. The first one is for initializing the accumulator R1 outside of the loop. The second one is related to the first point doubling in the loop when R1 is still in affine coordinates. Observe that in this case here, the time it takes for computing a point doubling is basically dominated by the call to BN copy. So we see a difference of 3 time slots in this trace here. And the same pattern cannot be observed on the case when the second most significant bit of the scalar is 1. Because no doublings in affine coordinates were performed inside the main loop. We can also take a look at how a similar attack can be mounted against binary curves. So now the attacker tries to detect if point R1 is represented in projective coordinates during point addition. The formula for point addition starts by multiplying the x coordinate of one accumulator by the z coordinate of the other. If R1 is in projective coordinates, this means that the Z2 value here will be non-trivial, and this field multiplication will be full. So it will be more expensive than the case when Z2 is trivial and has value 1. So the adversary will try to monitor the time between these 2 consecutive field multiplications to figure out if this value here is non-trivial. Again, the timing difference at first is not very large, but the performance degradation can amplify the difference to 100,000 cycles, corresponding to 20 slots of flush and reload attack, which allows the attacker to detect if the Z2 value here is trivial with larger than 99% precision. So again, the memory traces illustrate the attack. So we can observe that when the second most significant bit is 1, the first field multiplication will take a long time. So the second field multiplication only starts 20 slots later. This pattern is not observable when the second most significant bit of the scalar is 0 and the first field multiplication is fast and finishes quickly, and is then followed by the second field multiplication because the z-coordinate of the second input to point addition was 1, which led to a faster field multiplication. There are many software countermeasures that can be used to protect implementations against this attack. We list here at least 3 possible fixes. The first and most natural one is randomizing the z-coordinates at the beginning of scalar multiplications, such that there are no trivial values for z being operated inside the main loop. Second one is implementing the group law in constant time, for example, using complete addition formulas without branches or corner cases, but this imposes a performance penalty. The third possibility is implementing the Montgomery ladder over co-z arithmetic to not handle z-coordinates directly. We reported our vulnerabilities to OpenSSL in December last year, and they were ultimately fixed in April this year with the first countermeasure applied. The main takeaways of this part of the talk are that securely implementing cryptographic algorithms that are brittle is still very hard. Many things can go wrong in very subtle ways. In particular, it's important to not underestimate small timing leakage coming from insecure implementations, because an attacker may be able to find a way to exploit those and recover a long-term private key. In a more operational manner, we recommend everyone to upgrade to OpenSSL version 1.1.1 or version 3.0 when it's available as soon as possible. The development community behind OpenSSL has made a wonderful effort to improve the code base and its implementation security since Heartbleed, and we should all benefit from that effort. Now Akira continues the talk by explaining how the private keys can be computed from biased signatures using a solution of the hidden number problem.
Thanks, Diego. So hello everyone, my name is Akira Takahashi. I'm currently a PhD student at Aarhus University in Denmark. So in this part, I'm going to discuss how to exploit the ECDSA nonce leakage that we obtain from LadderLeak vulnerable implementations. So here's the overview. So the goal of the second part is to recover the ECDSA secret signing key by solving the so-called hidden number problem, which I'm going to define soon. So our attack essentially follows Fourier analysis-based attack, which was originally developed by Blahenbacher. So this attack method allows us to recover the secret key using only 1 bit of nonce information per signature. Also, in order to exploit the practical leakage information, our analysis also considers side channel attackers' misdetection of nonce bits. I want to remark that the techniques that I present here in principle apply to other sources of bias or leakage that are independent of LadderLeak vulnerability. So let's define the hidden number problem. So in the hidden number problem, the attacker is given the pairs H and Z that satisfy this modular equation. Also, the attacker is given the most significant bit information of nonce K. And then the goal is to recover the secret key Sk. So here, even though the equation doesn't look like an ECDSA signature, actually, once you obtain an ECDSA signature, you can easily convert the signature into an instance of the hidden number problem, like this. So why do we study the hidden number problem? So actually, the hidden number problem has been around for more than 20 years. And the fundamental attack method was already developed in late 90s. The first one is called the lattice attack, originally proposed by Hargrave, Graham, and Smart. And soon after that, Blahenbacher announced a completely different attack method called the Fourier analysis-based attack, which we study in detail in this work. So since the proposal of this attack method, there have been a bunch of real-world vulnerabilities that rely on the hidden number problem. For example, even looking at the last few years, we have seen many vulnerabilities, including cache code, port smash, return of hidden number problem, TPM fail, Minerva, the Java attack, and Raccoon attack. All these vulnerabilities essentially rely on the same hidden number problem. So concretely, by solving the hidden number problem, the attacker can steal the secret ECDSA key, or in the case of Raccoon attack, the attacker can steal the shared Diffie-Hellman key, shared secret key of the Diffie-Hellman key exchange. So this is why it's very important to study the hidden number problem and to evaluate the concrete attack cost in the hidden number problem. So as I mentioned, there have been essentially two different approaches to the hidden number problem. The first one is called lattice attack, which is more famous. So the lattice attack is known to work very efficiently if you have a relatively large amount of bias or leakage information. However, if the amount of leakage information is quite small, like 1 bit, then essentially lattice attack doesn't work. So in such a case, the other approach called Fourier analysis is known to work more effectively. However, the major bottleneck of this approach is that it requires too much data complexity. So of course, the main natural question is that can we reduce the data complexity of Fourier analysis-based attack? Also, we were interested in how far we can go. So more concretely, can we attack even less than 1 bit of nonce leakage? So here, less than 1 bit of nonce leakage means that the most significant bit information is only leaked with probability less than 1. And finally, we wanted to know whether there's such a small leakage coming from practical ECDSA implementations. In this work, we answer all these questions in the positive. So as a result, we managed to set some new records of the solutions to the hidden number problem. Here's a comparison with the previous work. So as you can see in this table, we essentially solved all these 4 cases. In the case of 160-bit HNP, compared to the previous method, our attack required fewer input signatures to complete the entire secret key recovery. Also, to the best of our knowledge, there have been no attack records against the 192-bit HNP. So here we set the 2 new records. So now I'm going to give you a technical overview of Brahenbacher's Fourier analysis-based attack. So the attack consists of 2 phases. The first phase is to quantify the bias of nonce k. So here we define some bias function such that it outputs something close to 0 if the nonce k is uniform in integers modulo the group order. On the other hand, this bias function should be something close to 1 if k is biased in ZQ. So here our first contribution is that we analyze the behavior of this bias function when the most significant bit of k is biased with probability less than 1. Then the second step is to find the candidate secret key, which leads to the peak of this bias function. In practice, this is carried out by computing fast Fourier transform. Also, even though I do not discuss in detail, there's actually a critical intermediate step called collision search of integers h. So this step is important in order to detect the bias peak correctly and efficiently. And actually, our second contribution is that we established unified time memory data trade-offs by applying a well-known algorithm in the symmetric key cryptology. So now let's define a bias function. So the bias function can be essentially defined in the form of discrete Fourier transform. So to get the intuition, it's always better to imagine a complex plane and a unit circle on it. So for example, if the nonce k is uniformly distributed, then we can imagine some corresponding vectors to those nonces. And those vectors are uniformly distributed in the complex plane. Then if you take the sum of those vectors, we can expect that the resulting sum is quite small. On the other hand, let's think about the biased cases. So for example, if the most significant bit of nonce k is 0, then we can imagine that those corresponding vectors are concentrated in the upper half of the unit circle. So in this case, we can expect that the sum of those vectors are much larger. So this is how we can quantify the bias of nonce, and also this is how we detect the bias, whether it is applicable. So in practice, we have to consider some erroneous leakage information. So let's begin with the easiest example. So of course, in an ideal case, if the attacker knows the most significant bit of nonce k with probability 1, then the attacker can collect the completely biased signatures like this. However, in practice, attacker sometimes makes mistakes. So the traces sometimes contain errors like this. So in this case, the erroneous leakage information affects the bias function. So this is why we analyze the behavior of bias function under the misdetection of nonce bits. And more concretely, we can estimate the absolute value of the bias function by this form. Moreover, we gave detailed trade-off studies in the complexity of the attack. So here, once you fix the curve parameter and the amount of available leakage information, you can draw these trade-off graphs. So these trade-off curves essentially mean that if you can spend more time on attack, then you require much less input signatures to complete the entire key recovery, and vice versa. So this is why if the attacker can carefully choose the point on this trade-off curve, then the attacker can always find the optimal balance between time and data complexities. Also, even though I focused on 1-bit leakage case, in the paper we also gave analysis for even more general 2 or 3-bit leakage cases. And we actually show that much smaller amount of signatures are needed to attack 2 or 3-bit leakage cases. And after analysis, we implemented the entire attack and show that indeed the key recovery attack works. So in the case of P192, the attack was made possible by executing our highly optimized parallel implementation in AWS EC2. And the entire attack completed in a reasonable amount of time. Also, in this attack experiment, we confirmed that the attack even works under some errors by using a bit more signatures than a non-error case. In the case of 163-bit curve, the attack complexity was actually much more modest. So in principle, you could even execute the entire attack against a 163-bit case in a small laptop. So the main takeaways of the second part are as follows. So as we show, ECDSA nonce is extremely sensitive. And especially even less than 1 bit of nonce leakage per signature is exploitable. And even though the hidden number problem is still old, this is still relevant nowadays because there have been a bunch of other vulnerabilities discovered by other people. So we can expect that in the near future, there might be some other vulnerability that stems from the nonce leakage of ECDSA. And after the analysis, we got multiple interesting open questions. So of course, we want to know whether it's possible to further improve time data trade-offs. So in our analysis, even though we managed to attack the 1-bit leakage, still it required at least millions of signatures. So of course, if you can find more efficient algorithm that gives better trade-off curves, then we might be able to further reduce the input data complexity of Blankenberg's attack. Also, we'd like to know whether there are other sources of small leakage that allows an attacker to learn 2 or 3-bit leakage under some errors. So we expect that in these cases, Blankenberg's attack works very effectively. So thank you very much for your attention. If you have any questions, we are happy to answer. Also, if you are interested in more details, you can find our paper in this URL.